All right, new week, new topic. Let's talk about functions and relations. So we have a lot to talk about. Even though you probably know what functions are by now, we can define them set theoretically, which is a new thing for us. And that makes everything very nice and specific and precise. And we can talk about like what it means to compose functions, what it means to put a bunch of them after each other, how to define them really. Let's get into all of that. Okay, so let's talk what is a function in terms of set theory, because we love set theory now. So let's pretend we have two sets, x and y, and here are their elements. I will draw a picture in a second based on these. So x has three elements, let's say, or three that I'm picking out to show you. x1, x2, x3. Yeah, let's say that this is the entirety of set x, and then here is the entirety of set y. It has four elements. A function is just a mapping. You take elements of one set to elements of another set. Potentially the same set, doesn't really matter. A function is just a mapping from one set to another. So let's say that our function f, let's define it to be, here's my function f in green, it maps x1 to y2. And maybe I should have drawn the y's in a different spot. I will regret if I do not change this. y1, y2, y3, y4, there. So let's say that x1 gets mapped to y2, x2 gets mapped to y1, and x3 skips over y3 and goes straight to y4. That is our function f. That's what it does for x1. It maps it to y2. F of x2 is y1, things like that. Okay? That is what's happening. That's what a function does. It takes some things to other things. All right? So you can specifically, or you can precisely define this function f as a subset of x cross y. So just a bunch of pairs, x, y, that say exactly where each element is going. So the function f, you can define it as this set, x1, x1, comma, y2, x2, it's getting mapped to y1, save that, x3 is getting mapped to y4, save it like that. So you can define a function just like this. That's all the information is needed to say who's going where, right? x1's going to y2, x2's going to y1. It all works out, okay? So you do have to be a bit more precise when you make a function. You have to remember that you got to map everybody in the first set, right? So for every x and x, if your function's going from x to y, you better know where everybody in x is going. They better have a place to go. That's a requirement for a function. There is exactly one y for which x comma y is in the function. Okay? So x is getting mapped, every x is getting mapped to a y. Yes? And the fancier terms for all of those are, the first thing is the domain. The thing that's getting mapped is called the domain, that set. And then the place that the domain is getting mapped to is called either the target or the codomain. You'll hear that mentioned. I'll use both terms probably. Target or the codomain. That's the set where you're mapping two things, okay? Notice that you don't have to map to everybody in the target or the codomain, especially if it's a bigger set than the domain. It's impossible, right? You can't hit everybody. So yeah, a function, deep down, set theoretically, it's just a bunch of pairs saying who's going where. All right? And let's see. We want our functions to be well-defined. That's a fancy term. So if f maps an element of the domain to 0 elements or more than one element, so if you have something like this going on, like if x1 also maps to y1 as well as y2, then it's not a function anymore, right? It's not well defined where x is going. Do you see that? I hope that makes sense. Same if like x3 goes to y3 and y4, that does not make any sense at all. Or if x3 went nowhere, that's again not a well-defined function. You got to tell me who's going where, and there can only be one place that each element is going to. Okay? So this is just our intuition with functions explained using slides. Okay? We want our functions to be well-defined, we say. All right? And finally, the final term that I'm sure you've heard before is the range. The range of a function is just all the things in the target/codomain that are being hit by somebody, okay? So it's all the y's such that xy is in f for some x. Okay, so we can define that too. So for example, the range of this function f, let's say range of f, that's equal to y1, y2, and y4. Okay? Notice that that is not equal to the target. That's not equal to the codomain. That's the whole set y, including y3. The range is just what's being hit by the function. Okay? So that's the main difference. Don't confuse these guys and this guy. And that's about all you need to know. So those are the first terms to get everything down and to understand what a function is. Let's have a bit more in terms of terminology. I'm sorry. All right. So let's first have an example, though. So let's pretend that we have a function that takes integers to integers. The target can totally be the same as the domain. Not a problem. Okay. And here is the function. It's defined to take every element to its absolute value. Does that make sense? It's just the absolute value function on integers. Okay. There are other absolute value functions on real numbers, on rational numbers. This one's just on the integers. So for example, f of negative 42 is being taken to positive 42. F of positive 3 is staying right there at positive 3. F of 0, the absolute value of 0, is still 0. So it's doing that. If you look at it on the number line, let's see what's going on. You have 0. It's taking all the positive numbers, the positive integers, right? Only integers, to themselves. So like 1's going straight to 1, 2's going straight to 2. But things that are negative, like negative 1, for example, is going to positive 1. It's doing this kind of thing. It's playing that kind of game. Okay? So I think you can imagine what's going on for the entire function now. And remember that you can have different functions. Let's make g go from r to r. Right? Where g of x is also defined to be the absolute value of x. This is a different function from f, right? Because the domain and target are different. G is allowed to map things like negative 3.14, right? To positive 3.14. F can't do that because it's only working on integers. Does that make sense? It's a different function. F does not know how to take decimal places anywhere. Does not know how to take real numbers that are not integers anywhere. Okay? So back to f. What's the domain? Integers, right? What's the target? Also integers. And then the range. What is the range? Dun, dun, dun. Notice that the only places that are ever being hit by the function, the only places that things are being taken to, are 0 and everybody over here. You see that? So, oops. So everybody who's being hit is on the right side of that number line, which means that the range is not z again, because it's skipping all the negative numbers. The range is all the numbers 0 onward, the integers from 0 onward, which are the natural numbers. 0, 1, 2, on and on and on. Isn't that cute? So yeah, the range of this function is just the natural numbers. I hope that makes sense. Let me close my email. Don't need that. So yeah, that is an example. Let's have one more term to define now. Functional equality. So we say that two functions are equal to one another if this is all true. If they have the same domain and target, they're taking the same sets to the same sets, and also for every element in that domain, it's being mapped to the same place by both functions. Okay? F of x is equal to g of x for every element in the domain, and because we know that they share the same domain and the same target, that's what it means for them to be equal. Okay, so that's called functional equality. That's when you can say that functions are equal to one another. Okay, let's have an example for you to try now. Okay, so here's a function, actually two functions, f and g. Figure out first the domain and range of these guys, and then tell me if they're well defined. Think about what that means, going back to this definition. If the function's doing weird stuff, it's not a function. It's not well defined. All right, so let's see. What are the domain and range of f? Let's talk about f up here and maybe g down here. So the domain of F is what set? It's all the things that are being mapped. Yeah? That looks like A, B, C, and D. And then the range, or let's do the domain of G too. Let's just do them both at the same time. Domain of G is, also A, B, C, D. Those are the things that are being mapped. A, B, C, D, and we assume that like there's nobody down here that we don't know about. All right, now let's talk about the range. What in the world is the range of F and G? Remember, the range is not the same as the codomain. The range is just all the things that are being hit. So everything that's being hit by an arrow. So it looks like W, X, Y, and Z for F. And then the range for G is W, X, and Z, no Y. See that? W, X, and Z, no Y. And then let's talk about well-definedness. So what does it mean to be well-defined? Well, every element of the domain better be mapped to exactly one element, right? You can't miss out, can't be mapped to 0 things, and it can't be mapped to more than one thing. If either of those are true, it is not well-defined. And so, look at B. B is being mapped to both W and Y. We can't have that. That is not a function anymore, so it's not well-defined. F. I hope that makes sense. Please yell at me if it does not. Let's talk about G now. Is it mapping every element to exactly one element? 1 to exactly 1, 1 to exactly 1, 1 to exactly 1. Yeah, it is. It doesn't matter that it's hitting the same thing twice for separate elements. That's still happening. That was fine, and that happened for our absolute value function, in fact, right? It mapped negative 42 and positive 42 to 42, positive 42. That's okay. It's okay to map different elements to the same element in the target. You can't do the opposite, though. Can't map the same element to 2 places or more in the domain. Okay, so this one is well defined. Okay, so hopefully all these terms are coming together with an example. Try this one now. Try functional equality. So here are 2 functions, F and G. So F takes a pair of integers, see that? That's the domain, to a single integer. So does G. So it takes 2 numbers, X and Y, and it gives back a single integer, the absolute value of X plus Y, okay? And then G also takes a pair of integers to an integer, and G maps, X and Y to absolute value of X plus the absolute value of Y. So that's the difference. What is being computed? Now, the question is, does F equal G? See if you can figure out the answer. So, what is required to have functional equality? Well, they better have the same domain and target, and all their elements better agree on where they're being mapped to. Okay, so we have to fulfill those 2 things. So we need the same domain and codomain. And we have that. You see that? We have that totally fine. And then we also need that the functions to agree on where they're taking each element of the domain. Now, do they agree? And I think if you try enough examples, you'll notice that they do not agree. So F of, for example, 2 and negative 2, and F and G of 2 and negative 2. Let's plug both of these in. So F of 2 and negative 2 is the absolute value of 2 plus negative 2. And G of 2 negative 2 is the absolute value of 2 plus absolute value of negative 2. So this is 4, and this is 0, isn't it? You see that? And those are not equal to each other, of course. So that means that the functions don't agree. So the final answer, does F equal G? The answer is no. Okay? Did you get that? Functional equality. If G had a separate, like, if G took real numbers, real cross reals to reals, then automatically they could not be equal at all, okay? Even though they're doing similar kind of stuff. The domain and target better match, okay? Can't be equal otherwise. let's talk about some terms that are very near and dear to our hearts as programmers. We use the floor function all the time when we do integer division. We just have never heard of it before, maybe. It's being done for us by the computer. But the floor operation is the one that is being computed. When you're doing integer division, it's chopping off all the decimal places, okay? So a floor function, the floor function, it takes a real number, so something with decimal places, to the nearest integer in the downward direction. So it never rounds up, it always rounds down to the nearest integer, okay? So it takes real numbers to integers, okay? And floor of x is the largest integer y such that y is less than or equal to the input x, okay? And the notation is kind of cute. It's just you take the number and then you like draw some walls, and those little indents are the floor. Isn't that nice? So for example, the floor of 3.14 is just go down to the nearest integer, positive 3. The floor of 42.5 is 42. It's not rounding up. It's always going downward. The biggest integer that is strictly less than or equal to x, okay? If you're already at an integer, it doesn't change. It's already there, less than or equal to, totally fine, 394, okay? And so this is what integer division is doing. This is what happens when you say static cast to an int of some number, 42.5. That's what this is computing. It's essentially doing floor for you, okay? So the floor rounds down, and the opposite is called the ceiling. That's the other metaphor. It rounds up. So that's the notation, of course, and it takes the input to the next biggest integer. Okay, so it's defined to be the smallest integer y such that it's greater than or equal to the input x, okay? That's probably the easier way to read it. And that is the notation. So ceiling of 3.14 is we're going up. We're going up to 4. The ceiling of 42.5 is going up to 43. The ceiling of 394, again, it's already an integer. Less than or equal to, it can stay at 394. Okay, so that's floor and ceiling. Ceiling goes up, floor goes down. All right. Let's use that in an example. All right, so let's pretend this is our example. A baker is packaging cookies for sale in boxes of 8. So there, you can only have 8 cookies to a box, and the baker has Y cookies to put into boxes. And because he has to put exactly 8 cookies into a box, the question is how many boxes total can he sell given Y cookies, okay? And the answer is going to involve either floor or ceiling. This is where it comes up in real life, okay? You kind of have to chop off things in a certain way. So think about it, and then we'll talk about it. All right, so let's pretend that y was like a multiple of 8, right? Let's say that y is 24 cookies. If that is true, in that case, how many boxes can the baker make? 3 boxes, right? If y is 25 cookies, he can still only sell 3 boxes. He's going to have 1 cookie left over that can't fit in a box. Does that make sense? So he can always sell y over 8 boxes, but if there are any left over, there will be decimal places with that, and we can't have any of that, okay? So we take the floor. Does that make sense? That is how many boxes the baker can sell. You divide it by 3, or divide it by 8, sorry, you get 3 point something, and you have to round it down always, because if you have just a few extra cookies that doesn't make another 8, that won't work out. So like if y over 8 was equal to 1,000.9999, you can't make it that 1,001th box, okay? That is unfortunate, but the floor operation says exactly what you can do in this situation, okay? All right, moving on to properties of functions. You've also heard of this before in a math class, but we're going to be more precise here. So if we have a function that's mapping x to y, we can say that it's a one-to-one function. Alternatively, we can say that it's an injective function if we want to get fancy in Latin. And this is what it means to be one-to-one. If x1 is not equal to x2, then f of x1 is not equal to x2. So reading this in English, f maps different elements in x to different elements in y. They never overlap. Okay? F never hits the same place twice, we say. So here's a function that is one-to-one. Boop, boop, boop. And boop, boop, boop. This is taking different elements, always, to different places. Let's have a fourth, in fact. Doesn't matter if you're leaving things out. It's just every element is going somewhere different. This is what it means to be one-to-one. If you have different elements, then they're going to different places. All right. The opposite of that is onto or surjective, and I'll get to that. Let me give you first an example of a function that's not one-to-one. Right. So here is 1, 2, 3, and 1, 2. We're kind of forced to have, let's say, a function that's not one-to-one if our target is smaller. So let's say that x goes here, or the first thing goes here, second thing goes here, and the third thing goes here. And let's call this x, y, and z. Let's call these a and b. So y and z are both being mapped to b. You see that? So this is not one-to-one because y is not equal to z, but f of y, calling this function f, but f of y is unfortunately equal to f of z, and they're not supposed to be. Okay? So, sad face, they're not one-to-one. This function is not one-to-one. Okay? So that kind of has to do with the domain. The domain kind of controls whether or not it's one-to-one. And so in that sense, onto or surjectivity is all about the target. Okay? Talking about the y now. And so what it means for a function to be onto is that you're always hitting somebody. For every y in the, you're always being hit. For every y in the codomain, there is some x that is taking, or that is being taken to you, to that y. So f is hitting every element in that target, in that codomain. So here's a function that's onto. Dun, dun, dun. 3, 4, 1, 2, 3. This is just a random function. It is onto. It doesn't matter that there's overlap. It's not one-to-one now, but every element of the target is being hit. Okay? Assume that this is every element of the target. All right? If you have a function that's not onto, that means somebody's not being hit. So a natural way for that to occur is if the target's bigger than the domain. So then you'd end up with something like this. And then this guy's left out. We don't have enough things to go there. Okay? So the function is not onto because not all the elements of the target are being hit by somebody in the domain. So that is onto / surjectivity, and comparing and contrasting that with being one-to-one or injective as a function. Okay? So these are both nice things to have. All right, and we'll get into that. If you have both at the same time, if you have a function that's both one-to-one and onto, it's a very special kind of function. It's called bijective. It's both injective and surjective, so it's bijective. And if you have a function that is bijective, there are plenty other terms for this because it's so nice to have. We have a bunch of synonyms for it. It's called a bijection, or it's called a one-to-one correspondence. Just a long mouthful. It guarantees that there is an inverse for that function. That's super duper nice to have, okay? So let's talk about a function that's bijective. Here's an example. Here is my domain, codomain, x and y. Boop, 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 boop. And so it is one-to-one, so different elements are being taken to different places, and it's onto, so every element of the target is being hit by some element of the domain. Do you see how there's an inverse right now? There's always a way to go in reverse. There's always a unique place to go from this y. Oh, it's this x that took us there. From here. Oh, it was this x that took us here. You can turn the arrows around and make another function. That is the inverse. Okay? So the inverse exists if you have a bijection. It's f to the -1. That's how we write it usually. And it's opposite. It goes from y to x instead of from x to y, right? So the inverse is just flip all the pairs. It is take x, y in f, every element that's being mapped to something, just flip them around, and you actually have another function, because you had this strong guarantees from being 1-to-1 and onto at the same time. Okay, so you can swap the input and the output, and try and think about, like, what breaks down when a function isn't 1-to-1, if it's not onto. What does that mean? Why does that mean the inverse doesn't exist? That's a great example to think about. So give that a try. And the inverse of f, I drew it dotted, but let's draw it in full, in green. It was going this way, right? Boop. And so I was going from y, sorry. And like that. Okay? So that's the inverse function for the original function. And it's guaranteed to exist if you have a function that's 1-to-1 and onto. It's kind of guarantees that your sets are the same size, doesn't it? So, here's something for you to try now. So try and find the inverse of these functions, if there is one, if it exists. Okay, so here's a function f that takes integers to integers, and it just adds 3. And then g does some stuff as well. Okay? So give it all a try. So, let's do a together. What is a doing, right? What kind of function is a? So it's taking integers to integers, so here's z twice. It adds 3 to every number, right? So, like, it's taken -3, there's more things above here. It's taken -3 to, like, 0. That is what f is doing. It's taken -2, it's also adding 3, right? It's taken -2 to 1. And it's taken -1 to 2. That's what's happening with this function. Is it bijective? Is it guaranteed to have an inverse? I think you can see, if you generalize this further, that yeah, there's always, it's definitely 1-to-1, and everybody's going to somewhere else, and it's onto as well, because everybody's being hit by some element. Okay, just go 3 up, or subtract 3, yeah? So that is quite nice. Let's see if we can find the inverse now, because we have just discovered that this function f is invertible. So what is the inverse? Well, how do we go from here to here? How do we go from here to here? You can kind of solve for it, right? Just replace it. So the inverse is something like x is equal to the inverse of x plus 3, solve for the inverse of x, yeah, is equal to x minus 3. Just go 3 away, and you're back to what would have taken you there through f. Okay, so there's the inverse. Inverse of f is x minus 3. Okay, so now let's do g. Is g invertible? Can you do stuff? So we can also try and solve for the inverse. So, like, replace everybody. So how do we get x out of this function? 2 times the inverse of x plus 34. Just swap them. Or this is like y and x. I just swapped x and y. That's how you usually find an inverse, right? But now I'm calling instead of y, I'm saying the inverse like this. And you can solve for this. This totally works. You get like x minus 34 is equal to 2 times g inverse of x. And so it's x minus 34 over 2. That is the inverse. Is this going to work, right? Is the question. So, let's figure this out. The issue here is you cannot go in reverse. Like, you can't swap these and remain z to z, right? Because when you have an inverse, it's going to flip these around and again take integers to integers. This is not always going to give you an integer. I hope that makes sense. So, like, g of 0, like the real function g, it takes 0 to 34, right? G of 1 is going to go to 36, right? It's going to be 34 plus 2. Where is 35, first of all? It's not being hit, so this function's automatically not onto. You see that? There's no way to hit 35. That's unfortunate. So that means, like, how would we get there? What's G inverse of 35? Well, if we filled in our problem like this, you could solve for it like 35 minus 34 over 2. And it's like, oh, if only I just gave 1/2 to G, then I would have gotten my answer of 35. But I can't give 1/2 because it's not an integer. So that is just a lot of words to say that G is not invertible. And if you wanted to give the best reason, I would say that it's not onto. Okay, it's not hitting 35. It does seem to be 1-to-1. Every value is going to something different, but it's not onto. It's not hitting everybody in the target. Okay, so G is not invertible, but F is, and that's its inverse. All right, so one slide more, and then we will have our break and let you think about things some more. So let's talk about composing functions. All right, so give this a try, and then we'll do it together. So function composition, this is when you take two functions, bring them together somehow. This is how you create a new function, okay? You make a new function by composing two other functions, and their types, their domain and codomain, they have to match up in a certain way, okay? And here's the way. So when you want to compose functions, you write it like this. G, and this is like the compose symbol. You usually read it as like the word after, so do G after F. It's a new function. It means apply G after F. It means do, where's a good place to write it? It means for every X, do F first on that X, and then do G right after it. Take that input. That's all it means. So that's function composition. Just make one big function, call it G after F on X. Okay? So that's how we're defining it. And here's an example. Dun, dun, dun. So here's F. It takes integers to natural numbers by using the absolute value. And here is a function G that takes natural numbers to true and false. It sees if its input is greater than 2 or not. Okay? And notice that it is allowed for us to do G after F. So first do F, that takes an integer, gives me a natural number. And if I do G, it's ready to take that natural number to a Boolean value. You see that? So G after F of -5 is G of F of -5, which is defined to be G of, what's this? That's the absolute value of X, so G of 5, and that is greater than 2, so it's true. So it all works out. Does that make sense? So this gave us a function. Well, let's write it all out. So F was from Z to N, and G was from N to Booleans, so N to true and false. And this needed to match up, and their composition ended up going from Z to the Booleans. You see that? We took an intermediate step in the natural numbers, but the final composed function takes an integer to a Boolean. I hope that makes sense. Took an integer, gave us back a Boolean. So, I also want to teach you one last piece of notation, the identity function. It's called I of A, and all it does, it's a special function that maps every element to itself. So this is the notation. The identity function on the set A goes from the set A to itself, of course, and it maps every element to itself. Very simple function. It's like, here's A, here's the set A, and here it is again. It's just taking every element right to itself. Okay, so like F of 5, or I don't know. The identity function on integers of 5 is going straight to 5. The identity function on integers of like 42 is going straight to 42. It's just taking the elements to themselves. That's all it means to be an identity function. And so let's use all that. let's figure out the way all of this is working. Okay, so here's some more examples. G and F. F goes from A to B, and G goes from B to C. What is the type, like what's the domain and codomain of G after F? So that's doing first F from A to B, and then going from B to C, and so it's combining these. Do you see that? So first it takes an A, and then it intermediately calculates a B, and then ends up with a C. So it's going from A to C. They overlap like that. And then, okay, what is F composed with G? F after G. So it's going to take a B, right, because you're doing G first, and then it'll give you back a C, which you're supposed to apply F to, but F doesn't take C's. What's B to like question mark? This is not well defined, or it's not defined. This function does not exist. You can't go in that direction, okay? And then let's bring some identities into the mix. Remember that the identity on A goes from A to A, and the identity on some set B goes from B to B. That's how that works. What is this function? What's it equal to? So the identity first takes elements of A to themselves, and then we apply F, which is expecting an A and gives us back a B. Well, all this does if you apply this to some A, well, the identity function's not really going to give back anything. It's just, okay, F of I of A on A, but the identity function is defined to give back A, so that's just F of A all over again. So F composed with the identity is just F. That's like multiplying a function by 1, kind of, the identity, okay? Or adding 0 to the function. Those are identity operations. So, okay, that works. What about this one? First do F and then do the identity on A. Does that work? F is from A to B, right? The identity on A is from A to A. Applying F to an A gives us back a B, and I of A is not ready for that. The identity function on A cannot have that. So this is not defined. What about this one? Identity function on B takes B's to B's, and then we need to apply apply F. That's going to take an A, but the identity function on B's gave us back a B. And so we're not ready to apply F right now. So again, this is not defined. Is that making sense? This one is, though. These match up. F takes an A, gives it a B, and then the B corresponds with what the identity function is ready to accept, and it'll just spit back out the same answer. So this is equal to F. Do you see that? So that is function composition in a nutshell. And I think we have some time to try this last example, so let's move that up here and let's do that this time. Okay? So the domain and the target of the functions f and h. Let's have these two functions as our examples, and let's pretend that their domain is z, so they're taking integers, and their target is also integers. So they're taking integers to integers, okay? So here's how they are defined. Can you give an explicit formula for f composed with h? F after h? Give it a try. See if you can find out, like, f composed with h of x is equal to something not involving, like, the letter f or the letter h, something involving x. Can you figure out what it's supposed to be? Alright, so if you're stuck or stumped, here is the way that you can try this out. You say f after h of x is, well, first do h, right? F after h. So first do h on x, and then apply f to the result of that. And let's expand. We know what these are. Let's expand that. So that is f of whatever h of x is, which, well, h of x is defined to take x to x squared plus 1. See that? And so now the input of f is not just a single thing, it's the whole thing, x squared plus 1, and we need to do 2x plus 3 from that. Okay, so it's 2 times the input was this, 2 times x squared plus 1, and then add 3 to that. See that? That's the secret. So it's going to be 2x squared plus 2 plus 3, so plus 5. And that's the final answer. So f after h of x is 2x squared plus 5. And that is an explicit formula, not involving f or h anymore, for f after h. Okay? So that is where I want to leave us today. We have talked a lot about functions. So in the next lecture, we'll get into the exciting world of relations, which is like a relaxed form of functions. So I'll see you then.